Okay, let's get started. Hello, let me also share my screen. Okay, great. Hello, welcome everybody. I'm very happy to have you all here tonight. I guess to start with, just to introduce myself, my name is Eleanor Harris. I am one of the co-directors here at the Clifton Institute, and I'm very excited to talk to you tonight about sounds in nature. I think this is the third time I've tried to give this talk, and the first two times no one signed up. So I don't know how I hoodwinked all of you to be here tonight, but I'm very happy to have so many people interested in learning about sound. And I think I saw some names I didn't recognize in the registration list, so I just wanted to say welcome to any newcomers to the Clifton Institute. We're very happy to have you. This is definitely kind of an anomaly, an outlier in the kinds of programs we offer. We do a couple Zoom programs a year, but the vast majority, the other couple hundred programs that we run every year, are here in person at the Clifton Institute. So if you want to come learn about how to identify trees or lichens or fireflies or mushrooms or how to nature journal or bird by ear, all sorts of awesome stuff, come and join us in person sometime. And since this is one of the few Zoom programs that we do, we're a little bit rusty, so apologies for any challenges with the Zoom. And I think there are it seems like there's two ways to chat, and we're going to ask everyone to use the Q&A rather than the chat, just so that there's one place that we can keep an eye on. And my husband and co-director Bert Harris is here tonight, as well as a panelist. And so he'll be keeping an eye on that, as will I, but Bert will be keeping a closer eye. And so if you have any technical difficulties, please put them there. I'll stop maybe halfway through to answer questions. If there's like an urgent question, I can answer that, but I'm going to try not to stop too much to answer too many questions, because we've got a lot to talk about. Okay, so let's get rid of a couple screens. Great. So we're here to talk about sound. This is a topic I have been interested in for a really long time. This is a picture of, I think it was my 4th grade science project, and I was testing the sounds made by different lengths and widths of guitar string. So it's something I've been thinking about and interested in for these 30 odd years. And here's a picture of me a couple years later playing a flute, the best instrument in the orchestra, as I will explain in a minute. And so I don't play a lot of music anymore, but I did for a long time. And so learning and thinking about sound and music has been a part of my life for a long time. And the other reason I think learning and thinking about sound is so interesting and important is that we are primates, like this simian monkey. We are primarily visual creatures. We really rely heavily on our visual systems. And primates are unique among mammals in that we have 3 cones, 3 types of color receptors in our eyes. There are other animals that have more, but among mammals, primates are the only one. And so there are mammals that would maybe see something like the grayscale on the left-hand column. They can just see light and dark. Our dogs have 2 cones in their eyes, so they can see the difference between yellow and blue, like it looks like in the middle column here. But primates are the only one that can see red, green, and blue. And there are a lot of interesting hypotheses for maybe why that is. It helps us see something like this bright red ripe fruit. So if you're a monkey scrambling around the trees, you can pick out a ripe fruit against the background of green leaves and unripe fruit. Maybe it helps monkeys see the patterns in each other's fur and kind of identify other members of your same species. Maybe it helps you pick out something like this leopard that's skulking in the undergrowth, so it helps you pick out predators. We're not really sure why primates have such good visual systems, but we do. And so I think it's very easy to kind of get locked into the way that we see the world. We're very used to relying heavily on our eyes. Of course, we hear, and I'm going to talk about some of the incredible things that our ears can do, but we definitely rely on our eyes a lot more than we do our ears. And so that means that we maybe don't think a lot about what it would be like to be an animal that relies more heavily on your ears. And it also means that maybe we're oblivious to some of the sounds that are going on around us. So it's nice to just kind of take the time to think about our ears and give them a little bit of time too. Let's see. Oops, sorry. So tonight I want to talk about what sound is. That's going to take a few minutes to just kind of explain what we're talking about when we're talking about sound. And then I'm going to talk about how animals hear sound, sprinkled in with some stories about how animals make sound. And so I just want to stop at the very beginning and say that if you are interested in this topic or you get interested after tonight, here are some books for further reading. My absolute favorite is An Immense World by Ed Yong. It's not just about sound, it's about all sorts of different senses, but it's a really incredible book, really written very well, super interesting. Favorite book about sounds, hands down. Another great one that's about sound specifically is Sounds, Wild and Broken by David Haskell. And this has to do a little bit more with kind of conservation implications of noise pollution, but also a really great book. A lot of what I'm going to talk about in how we hear birdsong I owe to this book, The Peterson Field Guide to Bird Sounds, written by Nathan Pieplo. There's also some really great online resources. So if you're interested in birding by ear, that's a great reference. And kind of at the other spectrum of animals, if you're getting interested in katydid songs like Bert is, we love the Songs of Insects by Lang Elliott. So let's talk about what sound is. Sound is a periodic disturbance in a medium. And a medium means for us air, but it can also be water, and it can also be solid objects. So that's kind of like a dry technical definition, a periodic disturbance in a medium. So let me show you what I mean by that. So you can imagine a tuning fork in a room. All of these little black dots are meant to represent air molecules. Of course, they're not at all to scale, but there's a lot of air molecules flying around this room. And imagine that I ping this tuning fork and the tines of the fork spread apart. And that causes a bunch of air molecules to kind of bunch up on each other. And there's a little bit of like this dense pocket of compressed air that's forming. And then the tines of the fork kind of contract, and that leaves behind kind of a vacuum. There's this area of space where there aren't so many air molecules. And then the tines expand again, and you get another pocket of dense air. They contract, you get a pocket of kind of vacuum, and so on and so forth. And you end up with this repeating pattern of pockets of air where there are lots and lots of air molecules, and areas where there are many fewer air molecules. So dense air, not dense air, dense air, not dense air, in this repeating pattern. And these packets are moving, in this case, from left to right. Of course, I really dramatically exaggerated the difference between dense air and not dense air. There aren't really any vacuums, but I just kind of wanted to represent the idea of dense pockets of air versus not so dense pockets of air. And so this is all sound is like little pockets of air moving through space. And we often talk about sound waves, and that's because waves turn out to be a really convenient way to look at these patterns of air molecules. And so we can draw something like this waveform at the bottom of the screen. And all it's meant to represent is the areas of space where there are lots of air molecules all packed up against each other. And then the valleys of this wave are the areas where the air is really far apart and there isn't so much air. And so just like there's dense air, not dense air, not dense air, you get this alternating pattern of peaks and valleys in this wave function. So that's all that sound is. And there are a few parameters of sound that it's useful to talk about. So the first is the wavelength of the sound wave. And the wavelength is just the distance between two of these dense pockets of air. They're often feet apart. So you might talk about how many feet apart are the pockets of dense air that are traveling through space. And like I said, these waves are traveling, so you also need to talk about the speed at which these pockets are traveling. So that's the speed of sound. So the speed of sound is just how quickly do these disturbances kind of propagate through space. And then the third parameter is, I think, probably the trickiest to wrap our heads around, and that's called frequency. And the frequency of a sound wave is just how often one of these peaks is going to pass by you. So if you imagine this sound wave kind of traveling from left to right, maybe it's going to travel right in front of my nose. The frequency of the sound wave is how many of these peaks are going to pass by my nose in a given period of time. So we usually talk about seconds, but it could be any unit of time. How often are these peaks traveling? So we have the wavelength, the speed of sound, and the frequency. And these three parameters are kind of interrelated. So a typical wavelength for a sound wave might be 2.5 feet. So the peaks of air might be as far apart as 2.5 feet, which is pretty far. And the speed of sound on average in air is about 1,100 feet per second. So really, really fast. These things are whipping by at really, really high speeds. And so just knowing those two numbers, we can figure out the frequency of this sound wave. So if you imagine one of these peaks traveling 1,100 feet in a second, zoom, it's gone 1,100 feet in a single second. How many peaks have gone by in that second? Well, you just take that 1,100 feet and divide by how far apart the waves are. So in this case, 2.5 feet. And you would find that the frequency is 440 beats per second. So we can always just find the frequency of a wave by taking the speed of sound and dividing by the wavelength. And it turns out that our ears are really tuned more to pay attention to frequency than they are to wavelength. So our ears respond to the frequency of a sound. And these are totally realistic numbers. So the speed of sound is about 1,100 feet per second. So really, 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 really fast. And the packets of compressed air coming by our ears or our head can be as many as multiple feet apart. So there are these kind of like huge waves being bombarded by all the time. So it's kind of crazy to think about literally any sound that you can hear is these waves just like hitting you in the face hundreds of times per second. So the speed of sound, like I said, is really just the speed at which vibrations spread in air or water or whatever object you're talking about. And it depends on the state of matter. So whether you're talking about the speed of sound in a gas, in a liquid, in a solid, those are all going to have different speeds of sound. It also depends on how elastic an object is. So a rubber band is going to have a different speed of sound than a block of wood. And the temperature is also really important. So I said the speed of sound is about 1,100 feet per second. It does change. It tends to get higher as the temperature goes up. So next time you're at like a 4th of July parade, you can have some pity for those poor marching band members who are trying to get their instruments all in tune under the heat of the blazing July sun. They're having some struggles that day because the speed of sound is changing depending on the temperature. And so I want to really emphasize that our ears are just rhythm detectors. All that they are doing is telling our brains, hey, I'm getting hit by repeating packets of air. That's the ear's only job. So they're just detecting vibrations in the air around us. And so if you hear my speech, but if you hear a note played by a musical instrument, you might hear a nice la, whatever note it is. That's just our ear's way of telling us that, hey, there's a vibration of a specific frequency out here in the air that I think you should be paying attention to. So it's receiving our ears are being hit by packets of air, and they're translating them into la, a pitch that we can hear. But it only does that, our ears and our brains only do that for a specific range of frequencies. So if the packets of air are not coming very fast, we might just hear a rhythm, a repeating rhythm of puffs of air. And it's only when those puffs get fast enough that our brains say, aha, I should turn this into a note or a pitch that we can hear. And so we can actually experience that shift between a rhythm of puffs of air and our brains turning that into a note. And so I found this toy online a couple of years ago, and I had to have it because it demonstrates this phenomenon. So this is called Space Crickets, and I think as far as I can tell, it's just like a glorified fidget toy. But what it is 2 balls on the end of this kind of flexible tweezer mechanism. And in a second, I'm going to clack these balls against each other, and they're going to go clack, 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 clack. They're going to hit against each other. And so that's just us hearing rhythm. But as the clacks get faster and faster and faster and faster, they just kind of speed up. They shift into the frequency where our brains turn it into a note. And so what's starting as a clack is actually going to shift into us perceiving a musical note. And so it's this shift between rhythm and pitch kind of happening before our eyes. So I hope maybe Bert can tell me if this is not working. We tested it earlier. I hope you'll be able to hear this. Let's go.
It's working.
Okay, great. So every one of those clacks, let me do one more. I hope you can hear that it's starting as clicks and then moving into this. That's the shift between rhythm and pitch. And so all the time, every time you're hearing a sound, our brains are already doing that translation for us. So that's just kind of a little peek under the hood of what's going on in our ears when we're hearing sounds. But why do our ears do that? So you can imagine like walking around this beautiful forest, like this forest here at Clifton. And it's not like there's going to be a tuning fork that's going to jump out and eat you. So why have we evolved to detect these packets of air hitting our heads? In general, it's advantageous for animals to be able to detect moving objects around them. So that might be they need to avoid a predator. That might mean they need to find something to eat. Might mean they just need to avoid some hazard in their environment. And it turns out that vibrations in air are a good way for them to do that. And there are some really great reasons to, for instance, hear sound versus seeing light. So for instance, life started underwater. So for millions, hundreds of millions of years, all life was swimming around underwater, and vibrations, in other words, sound, travels much farther underwater than light does. So if you were like a prehistoric fish and you wanted to detect a shark that was going to come and eat you, it might be better to hear the sound, the shark coming, rather than waiting to be able to see it. Sound actually also travels around and through objects better than light does. So you can think about being in your house and your husband's around the corner talking to you. You can hear him even though he's around the corner. So sound actually can move around objects in a way that light can't, and through objects. So this is why you can hear noisy upstairs neighbors, is because sound can actually travel through your ceiling in a way that light can't. So if you're in a forest or a cave and you want to be hearing things that are not within your direct line of sight, sound is a great thing to be paying attention to. Of course, it's also really great when it's dark out. We only have light when it's daytime and the sun is giving us light. So for animals who want to be hearing either in the night or all day long, sound might be better than light. And of course, there are animals who have figured out how to see at night, but sound is in general a better strategy. And the last reason sound is really advantageous is that at some point in evolutionary history, animals, quote unquote, decided that it was good for them to start to try to communicate with each other. So maybe they wanted to give each other information. And it is much easier to make sound. It is much easier for animals to vibrate their body like I am doing right now, rather than producing light. There are animals that can produce light, like fireflies, but by and large, it's much easier to vibrate your body. So if you want to be communicating, sound is the way to go. There are some challenges to detecting sound. So those are advantages of sound over light. Here are some challenges if you are primarily a listening creature. So again, imagine we have our tuning fork. It's sending out these vibrations into the air. And here's a puff of wind. A gust of wind is going to come. And since sound is just air molecules, it can disrupt those waves and make it really hard for us to hear that tuning fork in a windy environment. And that doesn't happen with light. Another problem with sound waves is, yes, they can go through and around objects, but they can also get bounced back off of objects. So if you can imagine a tuning fork kind of trying to make a sound in this dense forest, though the physical air waves might get bounced back off the trees and just make a muddle of whatever sound you're trying to hear. So that's a challenge of listening to sound. You can have wind moving the air around. Sounds can be bouncing off objects in ways that light is not. And maybe unsurprisingly, animals have figured out ways to surmount those challenges. Birds are some of the most vocal creatures around. And so we know a lot about their ability to both sing and hear songs. And so this is an awesome study of North American birds. And so you can imagine in a forest, you got all these trees where the sound waves might be bouncing around. So for one thing, maybe you don't want to be making really long, complex songs because they're just going to get garbled as they're kind of echoing and reverberating around. So maybe you want to keep your songs short, sweet, simple. You also might want to speak slowly, like I should be doing. Take nice, long pauses between the syllables to give each syllable a chance to get out there without being kind of all piled up against each other and echoing around. And so that's exactly what birds do. So these scientists looked at all of the bird communities in different habitats. And so in the red are open habitats, marshes, grasslands, shrublands. In the blue are forested habitats. And among the species that live in open habitats, many more of them have buzzy songs, and many fewer of them take pauses between their notes. Conversely, birds that live in the forest tend to not have buzzy songs, but tend to take long pauses between their notes. So, this is true of birds, probably true of lots of animals, that it's natural for them to kind of adapt the sounds they make to fit the constraints that are set by the habitat they live in. So I've been kind of talking about all these objects making vibrations, and we have to think about why so many objects are rustling and vibrating and making all these noises all around us. So why do so many objects make noise? And that has to do with something called resonant frequency. And I want to just pay a debt to one of my favorite online science educators, Steve Mould, who really informed the explanation of resonant frequency I'm about to give. So we'll do a simple thought experiment. You can imagine a box with a long skinny box with two rubber sheets on the end. So nice flexible rubber sheets that's full of air. We have a box full of air. And all we're going to do is bung, hit one end of the box. And just like the tuning fork, that's going to cause this compressed pocket of air to form. And that pocket of air is going to move down to the far end of the tube, and then it's going to bounce and come back. Now imagine that we hit the tube a second time before the first packet has come all the way back to the beginning. So now we have two packets of air moving around, and they're just going to be kind of like chasing each other around this box. And eventually they're going to kind of get muddled up and lose their energy and die out. And so we're not going to get any vibration going. However, if we waited to hit the box a second time until the first pocket of air had come right back to the beginning, now we have a doubly compressed pocket of air. And now this really dense pocket of air is going to travel all the way down, and then it's going to come all the way back to where it started. And you can hit it a third time, and now you have a triply condensed pocket of air that's going to move down to the end of the box and back. And so if you're hitting it just in time for the pockets to make it to the end of the tube and back, you're going to end up with this really stable, strong, self-sustaining wave. And that's all a resonant frequency is the frequency with which you should hit an object to get this really stable wave of air moving back and forth. And so it's going to look like this. At one end of the box, you're going to have really, really dense air. And at the other end, you're going to have very sparse air. And the dense pocket of air is going to move back and forth. So in a minute, it's going to be at the other end, and then it's going to come back to the beginning, and then it's going to go back to the far end, come back. And so it's forming this wave of not dense, dense, not dense air. And if you extrapolated that pattern to twice as long as the tube, you can see that this wave goes from a valley to a peak to a valley in a distance that is twice the length of the tube. So in other words, we are setting up a wave whose wavelength is exactly twice as long as the tube is. And you can actually hit it. There are multiple frequencies that can do the trick that set up these self-sustaining waves. So maybe hit the box the second time when the packet of air is at the far end. So I don't wait for it to come all the way back to me. I only hit it when the pocket of air is at the far end. And so now I'm going to have two pockets of dense air. At first, they're going to be at either end, then they're going to cross in the middle, then they're going to be at either end, they're going to cross in the middle. And you can see here that now we have this nice wave that goes from valley to peak to valley in the length of the tube. So this is another frequency that we can get the box vibrating at, and the wavelength is exactly the length of the tube. And there are actually many, many frequencies that we can use to get these resonant frequencies going, but what they have in common is that their wavelengths are always multiples of the length of the tube. So we can set up a wave that is twice the length of the tube, exactly the length of the tube, 2/3 the length of the tube, 1/2 the length of the tube, and so on, but exact multiples of the lengths of the tube. And that's all a resonant frequency is. It's a special frequency that you can hit an object to get these vibrations going. And if you think about, like, you've got a big gong and I'm going to hit it with a mallet, that one stroke of the mallet is actually introducing lots of vibrations into the gong, and most of them are going to die out, but the ones that are going to get amplified and make the gong go bong are the ones whose wavelengths fit the dimensions of the gong. And the longest wavelength that you get going this way is called the fundamental, and the higher frequencies are called harmonics. Let's see. And so what this looks like, we can look at this on a spectrogram. The lowest frequency is that fundamental. And then, so on the x-axis is time, on the y-axis is frequency. And so in that tube, you might have that fundamental frequency really loud and strong at the bottom in the dark black. And then as you go up the graph, you have all these harmonics that are getting fainter and fainter and fainter that are multiples of the lowest frequency. So just to recap, with resonant frequency, objects like to vibrate at wavelengths that are multiples of their lengths. And pretty much anytime an object starts vibrating, you're going to get multiple wavelengths at the same time. So most sounds are composed of multiple frequencies. And the one that we usually perceive is the lowest. And this means that in general, bigger objects are going to have longer wavelengths and lower frequencies. And smaller objects are going to have shorter wavelengths and higher frequencies. And so this explains, I've been talking about air tubes, and so this explains things like flutes, the best instrument. But the same thing is going on when a frog is calling, when a bird is calling. They're just getting vibrations going in the air tubes in their body, and then that kind of propagates out into the air. But basically the same thing is happening in physical objects like strings. So if you pluck a string, you're going to get a resonant frequency going. Or when you strike a gong, you're going to get a resonant frequency going. So when you strum a guitar, the strings start resonating and they start a vibration that goes out in the air. On a katydid, when they are making sounds by kind of scraping their wings against each other, the same thing is happening. A resonant frequency is getting going. It can also have kind of serious implications. So you might be aware of the story of the Millennium Bridge in London. This is a bridge that opened in 2000. It's a pedestrian bridge across the Thames in London. And it turns out that they built a bridge whose resonant frequency was about equal to the average step frequency of humans. So on opening day, everybody was excited to have a new pedestrian bridge across the river. Hundreds of people flocked onto the bridge, and enough people, just by kind of random chance, started walking in lockstep with each other in the resonant frequency of the bridge, that the bridge started oscillating. And then people had to walk in that lockstep to kind of keep their footing on the oscillating bridge. And then there was this feedback loop, and soon enough you had this bridge that was like silly putty. And thankfully everyone got off, no one was hurt, and they immediately went and added some weight to the bridge to change its resonant frequency. So it can have engineering implications as well. But so like I said, bigger animals tend to make deeper sounds. They also tend to hear deeper sounds. So this is the standard piano keyboard. This is about our hearing range. I said earlier that like a standard tuning note would be 440 beats per second. So there it is, A440, pretty much smack dab in the middle of the keyboard. That's 440 beats per second. Way down at the low end of the keyboard is the lowest note, which is vibrating at 27 beats per second, and at the high end, as high as 4,000 beats per second. And so we can divide the keyboard into octaves. There are 7 octaves in the keyboard. We can hear about an octave below the lowest note on the piano and about 2 octaves higher than the highest note on the piano. And then, of course, other animals have hearing ranges beyond ours. So elephants can hear a whole octave below we can. And teeny tiny animals like mice and bats who are using echolocation can hear even a couple octaves higher than we can. So again, you can kind of see a relationship between an animal's body size and both the sounds that it makes and perceives. Okay, so I want to talk a little bit about how we hear sound. So again, you can imagine walking around this beautiful forest. Maybe you're having a conversation with a friend. Maybe there is a bird singing in a tree. Maybe the tuning fork has jumped out of a tree again. Maybe there's an airplane going overhead. It is very easy for us to tell all of these disparate sounds apart. And that is really kind of an incredible thing. Because all of the ear is getting is pulses of air. So maybe this green wave is coming in from an airplane. Maybe this pink wave is coming in from a bird in the tree. But as far as the ear can tell, they're just coming in together, and they're definitely not color-coded. So the ear is just getting like puffs of air, and somehow it has to tell that some of those are coming from an airplane, some of those are coming from a bird. So one thing our ears can do is actually tell the direction that different waves are coming from. And so it can actually say, oh, I think I'm hearing a bird over here. I think I'm hearing an airplane over here. And that helps us kind of disentangle the waves, the puffs of air that are coming from different objects. But remember that pretty much any sound that is made is going to emit several wavelengths at once. And they are going to be multiples of each other. The wavelengths are going to be multiples of each other. And so if our ear hears waves whose wavelengths or frequencies are exact whole number multiples of each other, that's a pretty good indication that they're coming from a single object. But on the other hand, if even the waves are slightly out of sync, they're just slightly not exact multiples of each other, our brains are smart enough to know those multiple wavelengths cannot be coming from a single object. They must be coming from 2 different objects. And kind of like just with the space crickets, where we're going to hear this shift between rhythm and pitch, next time you go to an orchestra and you hear all the instruments kind of tuning up, you can also hear this shift between our brains thinking there are multiple objects and a single object creating noise. So as, for instance, a gaggle of flutes are all tuning up with each other, eventually they kind of tune in with each other. And if they can get as good in tune as possible, they might even start to sound like a single object, because our brains, as far as our brains can tell, they're just exact multiple wavelengths of each other. And we can't tell the difference between having 6 flutes or 1. But there is a lot of information in the spectrogram of all the different sounds that we're hearing. And our brains don't just throw that away. And in fact, it is the pattern of multiple harmonics that give us the quality of sound or the timbre or the color of different sounds in nature. So we can think about this especially in birdsong. If you ever go birding by ear, we use all sorts of adjectives to describe the bird songs that we hear. And so, we might hear a northern cardinal, and I'm going to play the northern cardinal. Here's the whistle of the northern cardinal. Do that one more time. So I might describe that as a sweet sound. It might be a pure sound. You could use the word whistle to describe that sound. That quality of kind of a pure whistle is our ears telling us that there's pretty much only one fundamental present. So you can see in the spectrogram on the left, there's just this dark band and barely any other lines on the graph. So there's one fundamental and barely any harmonics. And our brains turn that into this sweet whistle sound. In contrast, this prairie warbler has a very buzzy sound. And the reason it sounds buzzy to our brains is that you can see in the spectrogram in the middle, there are all these little wiggles. The frequency is changing really, really fast. And it's actually changing more quickly than our ears can kind of consciously perceive. And they just turn that wiggle into a buzzy sound. So let me play a prairie warbler song. So you can hear how raspy, buzzy, coarse, rough, a very different quality of sound from the cardinal, and that's due to the structure of the harmonics in the sounds that they produce. And then the last one I wanted to show was a white-breasted nuthatch. And so they have these really nasally sounds, and that's because of how many harmonics they produce when they sing. So you can see in the spectrogram, there are these kind of arch shapes all stacked up on each other. I count maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 harmonics all stacked up on each other. So there are multiple frequencies being emitted every time they make a sound. And for whatever reason, our brains kind of turn that into a nasal sound. So let me play the white-breasted nuthatch and you can watch the spectrogram. Let me do that one more time. So the cardinal to the prairie warbler to the white-breasted nuthatch to every other bird out there, the kind of quality, so not the note, but the quality or the timbre of their sound is due to all of these harmonics in their sounds. And that's also what causes the different instruments in the orchestra to sound different. So a flute is something kind of akin to that cardinal, the best instrument, because it just pretty much just makes a fundamental with very few harmonics. And a clarinet and a trumpet might look more like the white-breasted nuthatch with a lot of harmonics, so they add a lot of kind of a deeper, maybe a little bit nasally metallic sound. And so our ear's ability to kind of pull out all of this complicated information is what we have to thank for orchestras and human speech. And so all of the sounds that I'm creating right now are due to the harmonics. So I am able to move my larynx up and down a little bit. I move where my tongue is in my mouth. I move the shape of my mouth. And that all changes kind of the air tube that I am producing sound with. And it creates different harmonics in the different sounds that I'm making. And this is true for consonants and vowels, but it's particularly clear for vowels. So I'm going to play a recording of me singing 4 vowel sounds. I tried to keep the pitch as level as I can. So you can see the dark bands all the way across stayed as level as I could, but the harmonic structure changes over the course of the recording. Let me play some vowels. Let's see, let me do that one more time. So I was saying O, U, A, E. And as I go through those vowel sounds, you can see that, of course, entirely subconsciously, I'm adding more harmonics, and that comes out as a different vowel sound. So we also have harmonics to thank for basically all of human language. Okay, so let's get into the nitty-gritty of how animals hear. I'm going to focus, unfortunately for time's sake, mostly on vertebrates. And so across the board, animals with bones, vertebrates, use something called hair cells to hear. And so this is what they look like. They're just kind of bundles sticking up in the liquid of the inner ear. And the way they work also relies on resonant frequency. So all these hair cells have slightly different resonant frequencies. They're each tuned to a slightly different frequency. And when a puff of air comes in at just the right frequency, that hair cell gets going, it gets vibrating, and it signals a neuron that, hey, I'm hearing an A440. Hey, I'm hearing a high C, whatever note it is. And so they're just literal physical objects that get vibrating in our ear and communicate with our brain that they're hearing a particular frequency. And I'm going to talk about kind of the different structures that they're found in different vertebrates. So I just want to make sure we're all on the same page about vertebrate evolution. All life on Earth started underwater, and in the vertebrate family tree, we started as fishes. So you can see that on the left-hand side of this vertebrate family tree. The fishes were kind of the first kinds of bony animals. Hundreds of millions of years ago, the first fish started to crawl out on land, and they became the amphibians. And then more recently than that, mammals and reptiles split apart. And then finally, relatively recently, reptiles and birds split apart. So fish are kind of like the ancestral state of vertebrates. And then the other major groups are amphibians, mammals, reptiles, and birds. So since we started in the water, let's start with fish. Fish ears are relatively simple. They don't have any of these external structures. They don't have big flappy bits. They don't have tubes that bring any vibrations into their body. Their ears are internal organs, just like our internal organs. So it's just an organ sitting in their head. And when vibrations come in through the water, it just gets those organs vibrating, goes right through their head into their ears. They do have swim bladders, so they have these big air pouches that they use for buoyancy and balance. And in some species of fish, they're able to translate vibrations into their swim bladder into vibrations in their ear, but not all fish do that. But so for fish, hearing is a relatively simple proposition. They do have a problem in that fish are kind of just big, fleshy water sacs. Relatively speaking, their bodies are pretty similar density to the water that they're swimming around in. And so if a vibration is coming in through the water, it's going to tend to just get their whole fishy bodies vibrating at the same frequency. And that actually makes it hard for them to hear because they can't distinguish the vibrations in their body and outside their body, because at this point they're all just vibrating along with the water. And so they can't kind of disentangle the water vibration from their body vibrations. And so they've evolved something called an earstone or an otolith. And it's this is the picture on the right. It's kind of like a bone, but not quite. It's a calcium-rich deposit that they grow on top of their hair cells, and it's super dense. So when a vibration comes in and it gets their body vibrating, these earstones vibrate a little bit differently. They accelerate a little bit more slowly. And so they're actually able to tell the difference between how the earstones are vibrating and how their bodies are vibrating, and that turns into whatever frequency they're hearing. Otoliths are also just really important for marine biology. They're kind of like tree rings. So unlike bones that stop growing, otoliths keep growing an entire fish's life, and every year they put on a new ring of their otoliths, and so we can use them to age fish. Okay, so at some point a couple 100 million years ago, vertebrates started to crawl out of the ocean onto land. And this presented a whole new challenge. All vertebrates, our inner ears, those fishy inner ears that we evolved with, are full of fluid. That's no problem underwater where the vibrations are coming in through the water. It is a problem on land because water is a lot denser than air. And so it's really hard for an air vibration to get a little fluid sac vibrating. It kind of just doesn't have the oomph, the power to get a sac of fluid going. And so animals on air had to figure out how to turn air vibrations into vibrations in their fluid-filled inner ears. And so there's a couple of things that they did to do that. The first is that they redesigned one of their jaw bones. So fish, the skull on the left is a fish. They have this green bone called a hyomandibular bone. It's this bone that supports their jaw. Early terrestrial vertebrates shrunk that bone, moved it around a little bit, and turned it into something called a stapes. And you can see on the right in the green bone is basically a lever that translates vibrations coming in from the air on the right into vibrations on the inner ear cavity. So it's really just a lever that takes small, weak air vibrations and turns them into massive vibrations, saying like, hey, inner ear, we're getting some noise in here. And so they took one bone, shrunk it, redesigned it, and built themselves a lever to kind of amplify vibrations that were coming in the air. Another thing has to do, another modification that terrestrial vertebrates made was to modify their spiracles. And so if you've seen sharks or manta rays, you might have noticed these big divots behind their ear or behind their eyes. Kind of looks like an ear. It's not an ear. It's called a spiracle. Not all sharks have it, but ancestral fish all had these spiracles, and they're just a tube that goes from the outside of their body into their body, kind of close to their eyes. We don't really know what they were for. Maybe it was like a gill. Maybe it was like for a little extra water. Maybe early terrestrial animals were using it to breathe. We don't know, but they had these tubes called spiracles. So the other big modification that terrestrial animals made was to close off these tubes. So they closed off their spiracles and created the first eardrums. So they closed off these spiracles, made a big membrane that could collect vibrations coming in from the air, translate that into the lever bone, that then translated that into a vibration in the inner ear. And so the eardrums that we have are another adaptation that we have for listening to sound on air. And so if you look at something like this green frog, you see these big, beautiful tympanum, these eardrums. That's the outside of their old sharky breathing tubes. And that's their ear just kind of hanging out to the air. They don't have, again, they don't have any of these flappy ear bits. Frogs need to hear for the same reasons everybody else does, but in frogs, a big reason to hear is so that you can pick a mate. And so here we are in Virginia, we're at the start of the amphibian breeding season. These frogs, among others, are starting to sing, and they're making a lot of racket. So things like this wood frog on the left have started singing. I don't think we've heard any American toads yet. We have heard a couple spring peepers, and so they make a lot of rackets, and they need to be able to hear each other sing. You likely know that spring peepers are probably the most raucous of our spring breeding amphibians. They make huge noises, and they do something interesting, which is that male and female peeper ears are different. So males have actually basically become deaf to their own sounds. There's no reason for them to hear each other make such a racket. Females are still subjected to the poor females are still subjected to this really, really loud calling noise, but the males have shifted their hearing ranges a little bit too high. They can just barely hear each other, but not really, which is kind of a jerk move if you think about it. And there are studies that show that they kind of spread themselves out just far enough so that they can just barely hear their neighbors, but they don't have to listen to each other's rackets. And the females, meanwhile, are subjected to a whole lot of noise. But amphibians are very interesting because they undergo metamorphosis. So they start as something like a tadpole, and then they move into this adult frog. So here's a wood frog tadpole and an adult wood frog. And so, as long as I've known about metamorphosis, it's been, it's amazing to think about them switching from breathing underwater to breathing on air. They switch from swimming to walking. They have to lose their tail, grow some legs. It's an incredible thing. And before I started learning about sound, I never really appreciated that they would have to change how they hear too. So for the same reasons that, terrestrial vertebrates had to get new ears, just over the course of their lives, frogs have to get new ears. They grow their eardrums only as they metamorphose and come out onto land. Salamanders, on the other hand, don't do that. They never grow eardrums. We don't really know why. They have just lost the ability to grow their outside ears. They do still have inner ears in their heads, but they don't have external ears. And we're not even really sure whether they can hear or not. There are recent studies that show, yes, maybe they can hear a little bit, maybe they can hear certain frequencies, but there haven't been very many studies about it. And it's just one of those things that this seems like a very basic question. Can salamanders hear or not? But here we are in 2024, and we still don't know the answer. So someone has to go figure that out. Okay, so that's fish, that's amphibians. At some point, warm-blooded animals appeared on the scene. And like I said, all vertebrates have these fluid-filled inner ears. They're filled with this kind of thick, viscous fluid. And when the first warm-blooded animals appeared on the scene a couple 100 million years ago, that also threw a wrench in their hearing systems. Their body warmth actually melted the liquid inside their inner ears and made it too runny for them to be able to hear. and they made a change. So that's what's being shown in the left-hand graph is a bunch of living animals. Their body temperature is on the x-axis. Basically how runny their inner ear fluid is on the y-axis. And so the blue and the gray dots up in the top are mammals and birds, and they have really runny inner ear fluid. And so in response to that, they actually shrunk their inner ears. That helped them kind of hear a little bit better. And so now paleontologists, once we figured this out, paleontologists are able to go and use the size of a fossil animal's ear to try to determine whether it was warm-blooded or cool-blooded. So ears are kind of really important for a lot more of an animal's way of life than maybe we had understood previously. I'm not going to talk about bird ears all that much, but I do want to talk about how birds make songs. So we have one voice box in our throats. Birds have two voice boxes, one coming from each tube of their lung, and that gives them all sorts of acrobatic abilities. So again, we have our friend the cardinal, and here are its whistles without any harmonic structure, these pink to green down sweeps. And what this graph is showing, this figure is showing, is that in any given sound that a cardinal is making, it can actually switch between using the two tubes and the two voice boxes and the tubes from its lungs. So it's jumping back and forth between its two voice boxes all the time, and we're not even aware of it. And their two voice boxes are also responsible for incredible sounds like the ethereal, magical sounds of wood thrushes. So because they have two syrinxes, they're actually able to produce two sounds at once. And so that lends a huge amount of complexity to their sound. So birds are doing all sorts of incredible things with sound all the time. You've probably heard a dawn chorus. You've probably been woken by a racket of Carolina wrens outside your window in the morning. Birds across the world tend to make the most sounds in the morning, and kind of like whether salamanders can hear or not, why birds sing at dawn is another bit of a scientific mystery. We don't really understand why they are doing it. So maybe it's because it's a really calm time of day, and so like I said, turbulence can cause a problem for hearing. So maybe dawn is the nice, quiet, still time of the day where they can sing without too much disturbance. Maybe it's hard to forage when it's dark out, so they might as well sing, but I think we don't really know why they sing at dawn. So another mystery that someone has to go figure out. I just wanted to also add that feathers can make sounds too. And so if you want to hear some feathers making sounds this time of year, go listen to American Woodcock. Go find a shrubland. They have these special feathers on their wings that can make as amazing sounds as their mouths can. And it's starting to be mating season time, so go hear some woodcock wherever you are. Okay, so finally, let's get to mammals. This is another instance of evolution repurposing one body part for another purpose. A big difference between mammals and reptiles, who we've evolved from, is how we chew. So if you can think about a crocodile, they can pretty much just chew up and down. They're really good at chomping, but that's all they can do. On the other hand, if you can think of something like a llama or a cow, and they can do all these amazing things with their mouths, they can chew cud, they can masticate, that is a uniquely mammalian ability. I'm not sure we really understand why mammals needed to have much more flexible jaws, but that seems to have been a strong driving force in evolution. So we wanted to be able to chew more adeptly than reptiles. So that means that we had to redesign part of our jaw bones. And so the left-hand skull is a reptile jawbone, and the teal, blue, and red bones are all part of their jaws. And then the right hand is an early mammal, and they have lost the red and blue bits of their jaw bones, and they have repurposed them to be ear bones. So they took two bits of their jaws. We don't need that anymore. We want to be able to move our jaws more flexibly. We're going to put those in our ears instead. And so now, instead of just having one lever bone, we have three ear bones that translates the weak air vibrations into really strong liquid vibrations. These are the smallest bones in the human body. So you can see one of them here. This is our stapes next to a 10-cent piece. So teeny tiny bones, but they're really, really important for our ability to hear. Another mammalian innovation is our flappy ears. I think naturally when we think about ears, this is what we're imagining, the external ear. We're the only animals that have these big flappy ears. They're called pinnae. They're kind of like big radar dishes, and they help us collect sound. And they are hugely diverse among mammals. So you got dog ears, you got big old bunny ears, of course, huge elephant ears, bat ears that are specialized for echolocation. The graphic on the right is just primate ears, and you can see the huge amount of diversity that there is just among the primates. So another great mammalian innovation. Another mammalian innovation is our ability to suck. So mammals are the only animals that drink their mother's milk. This was a great idea, super nutritious, fatty, rich food that we can feed our young. But in order to drink milk, you have to be able to suck from a teat. And that turns out to be kind of a difficult thing to do. Most animals cannot do the sucking motion. You can't give an alligator a straw and expect it to be able to drink a milkshake. And so the first mammals that we know of that were able to suck were this, let me make sure I get it right, Microdocodon. These first early mammals 165 million years ago started to be able to suck. And the way they were able to do that was to reinforce their hyoid bones. So in the red bone on the left is our hyoid bone. You can feel it here at the junction of your chin and your throat, and it facilitates sucking. But it also facilitates all sorts of complex motions up here. And so our ability to drink milk is probably what's responsible for our ability to make all of the language noises that I am making right now. I want to just wrap up because I would be remiss if I didn't mention invertebrates, and especially insects. So insects need to hear for all the same reasons that all the other animals do. But there seem to be two major driving forces in the evolution of insects' ability to hear. So the first is that we have evidence from crickets and katydids that they started using sound to communicate as early as 165 million years ago. So that's a really, really long time ago. They're some of the earliest animals that we know of that started to use sound to communicate. And so once you start to be able to make sound, you better be able to hear what your friends are saying. The other major driving force in the evolution of hearing of insects was the appearance of bats. So bats first appeared on the planet about 65 million years ago. And as you know, bats are incredible voracious insect predators. And so all of a sudden there was this aerial predator zooming around and eating all of the insects. And so it seems like maybe the appearance of bats is what led a lot of insects to be able to hear to avoid these new predators. So insects' bodies are kind of like a big suit of armor. They have jointed bodies. They have joints all over their body and these hard plates of armor. From their heads to their thorax to their abdomens to their legs, they're covered with armor all over the place. And so it's quite a different body plan than us that have hard parts on the inside and all these fleshy bits on the outside. Because they're basically like a suit of armor, they have organs on all of their joints. It's called a chordotonal organ. And it's part of how they know where their body is in space. So at the junction of any two plates of armor, they have this little kind of flexible sheet that says, oh, I can tell that this arm is being bent right now. Oh, I'm relaxed. I bet that the arm is being extended right now. So they have these organs that help know where all of their plates of armor are. And they were very easy to turn into ears. And because they have these organs all over their body, they get ears all over their body. And it turns out that hearing evolved independently in insects at least 19 times. So all of these different insects just took a different body part and turned it into an ear. So mosquitoes and honeybees have their ears on their antennae. Katydids and crickets have their ears on their legs. Grasshoppers, closely related but have ears somewhere else, they have their ears on their abdomens. The vast majority of beetles do not have any ears at all, but a few scarabs and tiger beetles can hear. So tiger beetles also hear with their abdomens. Scarabs hear with their necks, as do hedgehog flies. So those are just a few of the different body parts that have been co-opted to be ears in all these different insects. And so it's just an incredible thing to think the next time you're hearing a katydid chorus that they're all listening to each other with their ears, which is a completely foreign way of hearing the world. Okay, pretty much an hour on the dot. I just want to wrap up with some of the takeaway messages that I hope you got. All that we're doing when we're hearing is perceiving the frequency of puffs of air. It's pretty weird. Our ears turn that rhythm of puffs of air into a pitch as long as it's in the right frequency. How we perceive the color or the timbre of a sound depends on all of those different harmonics that are being produced. There is this incredible diversity of ears out there. Go look up your favorite animal, and it probably has some kind of crazy ear that I didn't even get to talk about tonight. And like I said at the beginning, I just think we're oblivious to a lot of the sounds that are going on around us. So I hope we can pay a little bit closer attention and appreciate some of the incredible world of sound that's all around us. Okay, thank you very much. I see there's at least one question, and I am happy to take other questions. Okay, let me start with Jean's question, which is what kind of fossil evidence was used to determine that crickets and katydids used sound 165 million years ago? It's a great question. As far as I know, so the way that crickets and katydids make sound is that they have these kind of ridges. It's like one of those instruments, the like kind of grating instruments. They have these ridges that kind of scrape up against each other. And I think there's an imprint of the ridges of those wing structures on a rock in France somewhere, I think. So we actually have an imprint of the sound making body parts. Okay, another question. Were the hair cells shown in a slide all from humans? No, they were from different species. Good question. What do Lepidoptera use for ears? That's a great question, and I knew the answer yesterday. And I know that not all Lepidoptera, that's butterflies and moths, I know that they don't all hear. I think some of them use their antennae, and then there might be some that use a different body part. That's a great question that I'll have to look up.
I think on the butterflies, you don't have to be worried about scaring them off with sound. You can walk right up to a butterfly making noise. So that I guess they don't hear well, if at all.
And then, yeah, I think even within them, there's a good deal of variation. Okay, gang, I'll hang out in case anyone else has any other questions, but thank you again for hanging out with me, and I hope I'll see you in person. Oh, do caterpillars hear? That's another great question. I don't know the answer to that either. Do you, Bert?
Nope.
They're all over this. Yeah, insects. These wily insects. They're all over their bodies, and I have to imagine it's different in different groups of Lepidoptera. Yeah, so I'll hang out for another minute in case there are any other questions, but otherwise, I hope I will see you in person sometime soon.